Hi, how's it going? This video is going to have a fair bit of typing stuff. It's going to be long. I'm also recording this pretty late and I don't want to wake anyone up. Hey, fact is, what? It's 4 AM? You can't stop the Vulkan. You can't stop it. Okay, so here's what we've got right now. We run this and we've got 3D transformations. That's awesome. But I want to put textures on this. So there's a few steps involved. Firstly, we'll have to load a texture image in and then, well, go through the work of sending that texture image to our device memory. And then we'll have to basically do a lot of other work, set up our descriptors so that our shader knows that we're using texture, and then create a texture sampler which will grab UV coordinates and make the texture. Anyway, let's get on to that. So the first thing we need is a library to load textures. This is a project I was working on before. We grab this stb image.cpp and .h. And just paste them there. Then we can say add existing item and select the two that we pasted in. There they are. Now this is going in the home directory with the source code, so we don't need to worry about setting include directories, but we do need to include the stb. Cool. Okay. By the way, is this the weirdest tutorial ever? Whispering tutorial. This is ASMR Vulkan. Enjoy. So, what do we need? Well, we need to store the image and its memory. Okay, cool. Now let's create a function which will create this image. Okay, so a lot of the parameters here are very similar to the parameters we used to create the images in our swap chain. And actually, what we will do is we will take this create image function and we will abstract it. So we'll go back to the swap chain and edit it so it just calls this function. For that reason, I'm not going to go through explanation of these individual things. Hopefully they are self-explanatory. But the next step is we need to allocate memory for the image. Okay, so that's set up. Now let's create the specific image, the texture that we want to put on our triangle. Right, so what will it be? Well, I guess you know what it's gonna be. It's gotta be Noroi, the curse.
Noroi, Kurose.
This looks like a good one. Okay, so we'll just make a new folder. Textures and save it in there. Okay, so there's two things we're going to need. We've got a general create image, but we're going to need a create texture image. And we're also going to need to create an image view. Well, as a matter of fact, let's create all of the members that we're going to need. So we need an image view, we'll also need a sampler. Okay. In this line, we load the image and we return a handle to the actual pixel data. This is important here, so this will populate channels with the number of channels in the image. That's, I guess, from 1 up to 4, 4 being the full red, green, blue alpha. But this last argument specifies how we want to store the image. So big issue that I find when I'm loading images is if I don't have an alpha channel, it sometimes runs into trouble, but this guarantees that an alpha channel is created if one does not exist, basically. Nothing too crazy here. Width times height is the number of pixels. Each pixel is 32 bits, so 4 bytes each. Okay, cool. So this should be standard procedure. We create a staging buffer which the CPU can see because we need to send the data to the machine. But, of course, the memory which the computer can see is not the most optimal for rendering, and we're going to be loading this in once and reading from it many times, so for that reason it's beneficial to send this on to device memory. For now this is fine. So we create the staging buffer, we map, copy the memory over, and then we can free the image that we've loaded. The next stage will be to create the image that this is going to be sent to. So I'll just pop in here. Some of these arguments will start to make more sense when we actually use them in function calls. For instance, tiling. So tiling tracks how the pixels are laid out basically within the memory location. Linear is good if we want to be able to pick images like pixels specifically once they've been written, but optimal is good for just a standard operation, so we'll go with that. And then also note that once we load this in, we're going to be reading it with a sampler. So we state that we are using the sampled bit. Okay, so that's it. This will create texture image and image memory and allocate everything that we need to get the image there. So there is a bit more mechanism that we need to put in place because we can't just simply copy directly. We need to handle image transitions. Let me type this out, and this might make sense. So we want a function called transition image layout. Okay, so it's kind of like this. When the image is first created, it has an undefined layout. Now this layout undefined flag actually means a little more than that, but for these purposes, it's okay. What we want to do is we want to transition that newly created image from an undefined layout into a layout which is optimal for a transfer destination. After that is completed, then we will copy the image to the image data into that buffer, and then we will set it from, transition it from this destination optimal layout to one which is optimal for shader read only. Okay, so clearly the next goal is to actually create this function. Let's go ahead and make that. Okay, so this is the prototype of the function, but there's another thing involved. There's a lot of things involved in this. So what we would do is we would start a command, then run it, and then end the command. But that would be a single time command. Most transfers are single use commands. So because this will actually be happening quite a lot, we'll save some space by writing a general function to begin and end a generic command. Okay, so as you can see, this is pretty much just a generic code to start a single submit command buffer. We actually have this already, so we can actually update that. And that is in the copy buffer function. It's pretty much here. I could have just copied, but that's fine. Right, so while we're at it, we can actually pretty much grab this code, and that will be the code that we'll use for our end function. Okay, and this is fine because everything that we have is going to run on the graphics queue anyway. Okay, with that set up, we can continue. Okay, so the structure that we use to handle an image transmission is called a barrier, or an image barrier. As I fill out these fields, it will start to make sense how it works. Okay, so most of this should make sense, I guess, except for sub-resource range. So we're transitioning an image, but we might only want to transition a portion of the image. I don't know why, but here we're just going to go with the whole thing. And we're looking at changing the color, transitioning the layout of the color data, if that makes sense. Okay, so what I've done here is I am just manually checking which kind of transition we're doing. The access mask is the condition which must be fulfilled to go from the source stage, which is the process before the transition, to the destination stage, which is the process which will occur after the transition. So to set an access mask of 0 means no condition is set on beginning this transition. This pipeline, top of pipe bit, it's not an actual stage in the pipeline, it's what's called a pseudo stage. So it exists, we can query it, it's not a real thing. So what this is saying is after the pipeline begins, but before the transfer occurs, then transition the layout from undefined to transfer destination optimal. Now we can go ahead and check the other transition. Okay, cool. So we're checking these by hand. Here are two transfers which we could expect, and if we don't get that, then, I don't know, throw an exception. Why not? Cool. So now we can actually execute the barrier. Okay, dependency flags, none of those. Memory barrier count, no. Barrier properties. Memory properties, no, that's fine. Okay, no, we're not going to do that. Here we are. Image memory barrier count. We're sending in one of those, and we will go. Okay, so there's actually heaps of ways to do a barrier. Heaps of different data structures which can use it. Here we're using an image barrier. That's how we're doing it. Finish off the command buffer, and that's good. Okay, so now we can use this. So again, we transition the layout for transfer destination optimal, then we copy the image data, and then we transfer it to shader read. Okay, so in order to do this, we'll need a generic function to copy a buffer to an image. Okay, I guess we'll create that. Okay, so we describe basically how we're going to, which bits of the buffer we're going to copy to the image. And I know what you're thinking. You're thinking, hey, it might be 4 a.m., but have we lost our minds? Of course, this has these should be set to something. Well, if we set them to 0, then Vulkan understands that the data is tightly packed. In other words, we kind of don't need to specify these. It would just go, left to right, down row, down column, like that. Other important thing here is with this image offset, it's U, V, and W, so X, Y, and depth as well. But we just set that to 0, that's fine. Okay, then we execute this line here to copy that. Note that because the transition was already undertaken, we are in the right format, in the right layout to do this transfer. Okay, with that done, we can then destroy the staging buffer. Jeez, maybe I should go to sleep. I went VK destroy staging buffer, that's insane. Okay, let's press it. Okay, where are we at with this? Well, basically we've created the image, so it should be loaded into memory. And let me just double check that we're actually doing that. Okay, we've got that. The next step is to create the image view for that texture image. But first let's just run this and see that it even works. Hopefully this is it. So we need to add this other file, stbimage.cpp. And stbimage.cpp, it just has this line here, define image implementation. We could have even put that in our main file. That would have worked just fine. Let's see if this works. This is fun. Okay. Okay, so what I missed was we need to set the size that we're allocating for that. Okay, cool. So we've got this as normal. But just note that the memory usage is a little bit more because we've loaded the image in and it's good. So we need to now create an image view and then start, jumping into the descriptors. Okay, so we have this create texture image view, but we're kind of already creating image views, so wouldn't it be good if we could grab that code and make that into a generic function? So where are we doing that? Create image views, awesome. So we call this code inside this loop here, and that's basically creating an image view. So just grab it. And this won't be void, it'll be... What do we need? Well, we need to know what image we're talking about. Okay, so this is all fine. View type, yep. Format will be an argument for the function. And yeah, this is all okay. So we create it down here and then we return it. Okay, so how can we use that? Well, for our texture, we can say so then we need to fix up this function. Okay, the next step is to create a sampler. This sampler will pretty much work with the shader. So what do we have here? Well, we've already declared that we're going to be using a sampler, so now we'll make a function to create that sampler. Okay, so that's declared. We can also go ahead and call that after here. Okay. A lot of typing now, but we can do it. So as you can see here, the address mode is really the boundary behavior. And if you're familiar with OpenGL, it's the same thing with a different name. So we have UVW. The funny thing is this sampler can work with any dimension of texture. So we'll go with anisotropic filtering, basically anti-aliasing. Being mindful of my other systems, I'm going to go with a maximum of 4, but most video cards should be able to support 16 times filtering. Except my laptop, it turns out. Okay, so this is a little bit strange. Unnormalized coordinates is telling the sampler whether to expect coordinates to be normalized or not. If this is true, then we would access texture coordinates by their pixel numbers. But we don't want to do that, that's a nightmare, so we'll set that to false. And this means we'll be working with normalized coordinates where, for example, 0, 0 is the top left corner of an image, 1, 1 is the bottom right corner. It makes sense. So some operations involve comparisons, but we're not going to set this up. So we'll just set compare enable to false and just put in some basic function for the compare operation. Okay, so these last few arguments are not really used because we're not doing map mapping at the moment, but we will pass in some default values just so Vulkan doesn't squawk at us. Now we can go ahead and create the sampler. Cool, awesome, so that's created. So just another note here, most systems should support this, but we do have some options to check that they do. Okay, so we go to create logical device. We've got this device features, and these are the features which we are requesting. So what we're doing here is we're just specifying that we do want to use anisotropic filtering. We can also alter our check here. So we grab from our physical device the set of supported features, and our final test is, does all this stuff work, and do we have sampler anisotropic? Because when we call this, all these fields including sampler are set to Boolean values, so we can just query them if they're supported. Okay, next step is we need to set up our descriptor set layout in order to work, basically. So most of this is self-explanatory. This immutable shaders, set it to a null pointer, that's fine, we just have to do that so that things work. But yeah, this is called a combined image sampler, and the way I've conceptualized this is it's a combination of both the image data and the sampler which works on it, which is what that means. At least that works. So now what we need to do is we need to grab both of these layouts, these bindings, and pass them into the structure. Yeah, I know, it's 2, right? But we're going to make this as generic as possible. Okay, so now we go to the descriptor pool, and we need to update that as well, because we basically need to be able to allocate both a uniform buffer and a sampler from the pool. Okay, then we go to the, what have we got? We've got descriptor set layout, we've updated descriptor pool, we need to go to create descriptor sets. So this is actually the step of combining the image and the sampler together to make a combined image sampler. Okay, cool. So I'm trying to hurry it up. It's late. I'm tired. Let's finish this. Let's get this show on the road. Okay, so now what do we have? Our image is loaded and our shader is actually expecting to have the image and sample it. Of course, we need to update our vertex data. And we need to create an attribute pointer to it. Okay, cool. So then we'll update the vertex data that we have declared down below. Whoops, I missed something. So we are now expecting 3 of these attributes. Okay, awesome. We're so close. Now we just need to update our shaders. Okay, cool. So we pass the texture coordinate through with no transformation. And then for our shader, our fragment. Okay, let's leave color out of it for now. Let's just go. Okay, cool. So what we're doing is we're just sampling from the texture and writing that to the screen. Now, of course, we've gotten ahead of ourselves because we need to be a good memory citizen and clean up all of our structures, not structures, but all of our things we created. So we'll just go back down, finish that off, and then we'll get this done. Okay, hopefully that's everything. Cool. Okay, so now we can run this. Of course. We need to compile the shaders, so we go to the shaders and run the compile script. This should be updated. Well, that's not great. What a thing to miss. So, it turns out in the vertex, these should all be binding 0 and they should just be changing their locations. Finally. Okay, so just double check all your code, but have a look. This isn't great. I mean, if we open the other image, it definitely looked a lot brighter. So what's the problem? Well, hey, maybe if we load a brighter image, it'll work better. Let's see. Oh yeah, this looks like a good image. Okay, let's try that. And it still doesn't work, still looks too dark. As a matter of fact, the original image was far too dark anyway. So the answer is we need to perform gamma correction on this image to brighten it. That's the short answer, basically. So here's how gamma correction works. Okay, so this basically just sets up a response curve, which is more favorable. Makes the lights a little bit lighter. So we can go ahead and compile the shaders. And, give it a shot. Okay, so I was trying to compile the shaders, but they weren't compiling because errors were happening, but because I was double clicking it wasn't outputting the errors. However, if we run this within some sort of shell, it captures the errors, and we see that we missed a capital C. So if we compile again, then the fragment shader compiles, and there it is with gamma correction. Image now looks proper, well, a little stretched, but proper. We can also incorporate color again. And there we are. We have color. Here's the disco. We can also go back to the original image. Doesn't matter. And it should work just as fine. There's a bit of color in there. It's not so bright though. Okay, cool. So that'll be it for now. Hope you had fun. I know I did. I'm going to edit this down as best I can. It's been about 2.5 hours of recording. Oy, crazy. Alright, have fun. See you next time. Bye.